Hi everyone. So today we're going to be working with what is called families of functions. It's kind of an introduction before we get into talking about quadratics. So all the equations and graphing that we're going to do from this point on represent in families. So we're going to talk about quadratics, and quadratics is a family. We're going to talk about polynomials, and we're going to say those are families. We're going to talk about logarithms. That's a family. So I wanted to talk about families first before we get into the individual families that we're going to talk about. So in our families, we have to talk about what exactly is a family, what is a transformation, and we're going to spend more than one day on this because it's how we're going to be able to do what we do later on. So it's kind of like the base of almost all of the graphing that we're going to do. Polynomials is a little different story, but it's going to be a lot of the basis of what we're going to be graphing. Okay, so we're going to analyze what is called the transformations of functions and talk about families. So families of functions are the sets of functions in which each function is a transformation of a parent function. Okay, so these are, like I said, families. So things like y equals x and y equals 3x plus 1 is part of a family. They're all linears. Things like y equals x squared and y equals 2 times x minus 2 quantity squared minus 1 is part of that family. And the same when we talk about polynomials, okay, or square roots. Let's say f of x, remember f of x is the same as y, might be the square root of x. So a part of that family might be f of x is equal to 2 square roots of x plus 1 minus 3, okay? So they're all along the families, okay? So you have what is called the parent, and then you have all these transformations that occur to the parent. So the parent is the simplest form in the set of functions that form the family. Each function in the family is a transformation of that parent. So y equals x is the parent for linear, because that is the most basic function. Y equals x squared is the parent for quadratic. Okay. Now, polynomials doesn't really have a parent because you have y equals x cubed, y equals x to the fourth, and so on. Those are parents of those specific cubic and quartic and families like that. You have y equals the square root of x for the square root functions. Okay. You have y equals a base to the x for exponential functions. Okay, so there is a whole slew of families that we're going to be talking about, but everything is based off the parent function, which is the original with no adding, subtracting, multiplying, or dividing applied to that function. Now, the transformation is a movement. So in other words, we're going to take the parent function and move it left, right, up, down. We're going to stretch it. So is it a scale? Is it a vertical compression? So did I elongate it? Did I stretch it horizontally? Those are transformations. Okay? So you have different transformations. You have translations and you have scaling, or what I may recall to shifts and compressions, vertical compressions, and my brain just went. Compressions, what's the word? I just lost it. Stretch. I don't know why I couldn't think of that. All right, so it's the movement left, right, up, down, and the vertical stretch and compressions. Okay, so if I start out, let's say, with y equals, the absolute value of x, that's a good one. Then a transformation might be adding something inside the function or subtracting something on the outside of the function. That's a movement because we're going to move the y equals the absolute value. Okay, so we're going to talk more today and Monday, today in our next class period, about these transformations and what they look like and being able to write equations and be able to talk about what they do to the graph. Okay? All right, so let's talk about shifts, or what would be translations. Okay, another word you're going to hear for shifts is translations. There are two types of shifts or translations. There's a vertical shift left and right, and then there's a vertical vertical shift up and down, and a horizontal shift left and right. Okay, so let's just start out with just looking at it visually. So how are the functions f of x and f of x minus 2 related? So I'm going to go in my calculator here and put in y equals x. Okay, so there's our graph. Okay, we can see it's a nice slope of 1. Okay, there we go. That's a better picture. Linear equation. Okay. Now, if we add in, or if our next equation is x minus 2, that's the orange one, what happened? Okay, well, it moved. The green is now the orange one is the moved function. So there's two ways we can think of this, and that's just the nature. See how we can move it? Do you see how it went from 0 to 2? And went from 0, and now we're down 2. That's the shift. Okay, so this graph moved. I'm going to like the up and down shift 2 units down. You can also say 2 units right. Which doesn't make sense because it's minus. Why would you go right? There's a reason for that. We're going to talk about that in a minute. Okay, so we're seeing a shift in our line. Okay, either it's moving 2 units right or 2 units down. Okay, so we got this idea. It's moving. I'm not quite sure which direction it's moving yet. Well, let's try another one. Okay, let's do x squared. Okay, so let's go into x squared. And we're going to do x squared. Okay, so there's our quadratic. It's U-shaped. Okay, so let's try the next one. Okay, so we have plus 4. Now we definitely can see a movement up. Okay, so these two are related. They're exactly the same, except the second one, the graph moved 4 units up. Okay, in fact, the vertical shift, okay, up, down, right, is actually the function. We'll call it this. Okay, we're going to say the function, and we're going to either minus, we're going to use the letter k, or the function added a k. Now, when I say the function, it's basically taking the parent and either adding to the outside or subtracting to the outside. Okay, so we're going to take the parent function and either add to it or subtract to it. Now, your horizontal shift, I thought we'd do like an application of why this works. So the graph here is a projected altitude, f of x, of an airplane scheduled to depart at the airport at noon. So the black one is the airplane leaving at noon. Okay, so 0 meaning hours after 12 noon. So it leaves on time, it goes up, it's flying, there's our horizontal, like nice cruising altitude, and then we come back down and land. If the plane leaves 2 hours late, what function represents this transformation? All right, so let's think about this. If we're supposed to leave at 12 noon, but we don't, and we leave 2 hours later, okay, notice that we shifted 2 hours that way. Okay, so we shifted 2 hours to the right. But we're late, so we're subtracting 2. Okay, now I know that doesn't make any sense whatsoever because we moved to the right, but why are we subtracting? Because we're late. 2 hours after the time, supposedly from the time they were supposed to leave. Okay? In fact, horizontals, we're going to call this H. This guy moves right, and this one moves left. Okay? Oh, by the way, this one moves down, and this one moves up. Okay. All right. Okay, now that is our shifts. Okay, we're going to move either up, down, or left, right. Now, inside the function, when we take the function and we're going to take the entire thing, we're working within the function, it's always opposite. Okay, and I know that's hard to put your head around, like, why can't we just go the direction it says? Trust me, when we look at the actual, let's say, form that we're going to use, it's going to make more sense. All right, so let's talk about stretch and compression, or as this is scaling. Okay. All right, so there are actually three things. You have a reflection, you have a vertical compression, and a vertical stretch. Okay, so let's talk about reflecting. Reflecting flips the graph of the function across a line, maybe an axis, or y equals x. Each point on the graph is a reflected function is the same distance from the line of reflection as the corresponding point on the graph of the original function. Okay, so the gray, is the original function. If we reflect across the y-axis, okay, we're going to reflect across the y. That means we're going to go this way. Okay, each point is the same distance from the y-axis. So it's almost like taking the y-axis, taking the function, folding a piece of paper along the y-axis and matching it up. Okay? It's a mirror image. It's not like we took it and pulled it across the x-axis. It's a fold. It's a mirror image. So notice that, let's say this point 1, 1 is now over the y-axis, so our x value became negative. We're still at the same y value. Our 3, 4 became -3, -4. Our 5, 1 became -5, -1. Our y value, our x values became negative because we flipped it across the y-axis. So we went from positive x's to negative x's. Okay. If we were going to reflip over the x-axis, again, take a look at the values. All right. Here the y's changed because we went from positive y's to negative y's when we went from first quadrant to fourth quadrant. All right, so the reflection, you have two possibilities right now. We can talk about y equals x and other ones later. That if we're going to reflect over the y, our x values change. Make sure I said this right. I don't want to give us the wrong. Oh, nope. Yep. Okay, so we're doing opposite of x. Okay, the x values change. That we reflect over the x, our y values change. Remember, f of x is the same as y. So it's the opposite of the x values or the opposite of the y values or opposite of y. Okay, remember, f of x is y. All right, now, vertical stretch. Okay, when we talk about vertical stretch, I kind of put this in here. There's our picture. Okay, there are two kinds. So a stretch is like elongating it vertically. Okay, so we're kind of elongating the graph vertically, but it's still anchored on the x-axis. Okay. So it multiplies all the y values of the function by this value bigger than 1. So here we're going to multiply the y values by a value greater than 1. So we're going to use the letter A here to represent this. So A is greater than 1. So this would be A times our function. Okay? So if we look at this picture, okay, the blue is the original. The coral, I guess, notice it's stretched. It pulled up. Okay? Now, that's called a vertical stretch. We're stretching the function. The vertical compression is that we're going to be multiplying or reducing all the y values by some factor. So we're going to reduce the y values. Okay, by a factor between 0 and 1. Okay, so for example, again, we're going to use the letter A. So A is going to be between 0 and 1. Okay, so this could be a fraction. Okay, things like that. That could affect it. All right. So I don't want to use the word fraction because like 3 over 2 is a fraction, but it's still bigger than 1. So think of it as between 0 and 1. Now, why don't we do anything less than 0? Well, less than 0 would be a reflection. So, like I said, there's 3 parts. You have your reflection. So if we have a negative involved, that's a reflection. And then you have the multiplication of the number in front. So you're either going to have an integer or a number bigger than 1 in front of your function, or you're going to have a number between 0 and 1 in front of your function. So if it's negative, you have to separate that out and say that's a reflection. Then the number tells you whether it's a stretch or a compression. Okay? All right, so here's a summary of everything we just said. Okay, so you have your vertical translation, so you're going to add k or subtract k. You have your horizontal translation, which either you're going to go inside the function or outside. Inside the function by subtraction moves right. Addition moves left. Okay. Vertical stretch is when your number is bigger than 1. Vertical compression is when your number is between 0 and 1. The reflection over the x is when the negative is outside the function, like maybe it's with your vertical compression. And if it's across the y, you're going to see it inside the function. Okay? All right, so let's take a look at some examples. The graph of a function f of x is stretched vertically by a factor of 2, then translated 3 units down. What's the equation? Okay, so here's our vertical stretch because we're multiplying by 2. So we're going to go f of x is equal to 2x. And then we're going to go translated 3 units down, we're going to go minus 3. Okay? All right, so there's our equation. All right, let's try the next one. What transformations change the graph of f of x equals x squared to the graph of g of x? They just gave it a different name, of x plus 4 quantity squared minus 2. Okay, now if you're not sure, let's put it in our calculator. Okay, so we have x squared, and then it's x plus 4 quantity squared minus 2. Oh, wow. Notice that the orange one is now 4 units left and 2 units down. Okay, so it did move the graph. Okay, so that's what we're going to say. Okay, the plus 4 moves it left. So we moved 4 units left. And 2 units down. Now I know it seems a little confusing, and how are we going to use this? So you're going to see that on the next time we meet. We're going to work on this again next time we meet, and talk more about transformations. All right, guys, have a great rest of your day. Please stay safe out there, and I'll talk to you again real soon.